first of all, I'm going to tell you a little bit about some star formation. This is, of course, that beautiful Eagle Nebula that everybody's familiar with. The pillars of creation, some people called it. And on the left-hand side, you can see sort of a typical color image of it, and that dark dust and gas that you can't see through. And the pillars are being eroded away by bright, young, hot stars that are kind of eroding that gas and dust away. Now, if you look in the infrared, however, the infrared's the right-hand side, you can peer through that gas and dust and you can see the stars. Now, a lot of stars are being formed there. This is a region of active star formation. So we want to understand that star formation. And that's what that video you saw to open tonight's program was all about. You have hot young stars in the middle, you have hydrogen, you have H2 regions, which is ionized hydrogen gas, where the electrons have been stripped off, and it's this interaction with the magnetic field that make this so interesting. Now, this diagram I had to put in, I know it's a little janky, but this was from Mike Bolte. He was one of my professors at Santa Cruz, and I love that my staff found this for me. I didn't pick it, but I kept it because Mike Bolte was one of my professors at Santa Cruz, and terrific guy too, wonderful astronomer. Anyway, this is the basics of what went on, and these quick drawings, by the way, were done by our very own Chris Butler, so we can thank him for Griffith Observatory originals. You start with a big molecular cloud, mostly hydrogen and helium, and the stars somehow collapse. That collapse gets started off, and you make these young stars. Well, the energy from them can create a shock wave, and we thought it would trigger more stars, where that little arrow forming more stars in that shock region. Well, the stars that formed will kind of drift away, form an open cluster, drift away from that molecular cloud in the background, and then eventually form an older open cluster. The question is, when we do a simulation, do we get the right ratio of stars? Do we get enough big ones to small ones, enough medium-sized ones? We weren't getting that right. It was difficult to make the right kinds of stars in those simulations. So that one you were watching was called Starforge, and they decided they were going to add in magnetism, they were going to add in jets. Those jets you saw coming off the stars were all simulated, and they had to use a supercomputer, of course, to be able to get this done. Lots and lots of hours on the supercomputer, and it made a simulation, of course, that looks something like this. Now, do I need to click on this to make it? Oh, there it goes. Perfect. And you can see the gas starts to get pulled together. The magnetism within there drives the direction it moves. Star formation gets triggered. Energy starts to get piled into this gas and dust. And those jets start to shut down the star formation. They notice that the jets can actually quench the star formation and make it kind of shut down. There they go. They're those jets that I was talking about. They'll shut down that star formation and turn it off. So we get a zoom in here on the jets, and they're able to simulate these in these supercomputers. So zooming in here, one more forward. You can see there, looking at the very, very largest sizes there. That's their whole simulation. You can zoom in on a smaller pocket and then continue to zoom in until eventually you're in the upper right, that sort of S shape that's up there. That's the jets coming off of that. And those jets do shut down the star formation, but they still had a problem. They were making stars that were too massive. The biggest stars we see are around 100 solar masses or so these days. Something about their simulation wasn't doing that quite right. Now, maybe we can get informed by reality. This is a real star cluster. This is a cloud of gas, a molecular cloud, a giant molecular cloud forming stars. Some astronomers said, well, let's study it and let's study the magnetic fields there. In fact, this is kind of a joke, to me at least, and to a lot of astronomers. For the longest time, you'd go to meetings and people would say, well, we're having difficulty simulating the gas movements within the galaxy. We're having difficulty simulating the star formation. And someone, you know, okay, I won't call them the name that people would call them, but eventually someone would raise their hands and say, have you considered magnetic fields? And people would say, of course I haven't considered magnetic fields. They're too hard. Well, they're no longer too hard, and people are doing this within their simulations. So it's pretty exciting that this is going on. Now, these folks aren't simulating it. They're measuring what the magnetic fields are actually doing around these complexes. So these little dashed regions, those are where they're finding stars that have formed. The gas is there. The dust is there. Well, you can use something called a polarimeter to measure the polarization. Polarization is like your fishing glasses or your sunglasses for driving. They have some of them have polarized filters in them. And if you turn them, you'll notice the brightness of reflected objects will change. Well, they do the same thing here. They turn the polarizer and take many, many different pictures at different angles, and they can see where that light is getting reflected and how the magnetic field affects it. And here it is. The yellow lines, the length of them is the strength of the magnetic field. The direction of the line is the direction of the magnetic field. So you can see how, let me get my little pointer out here, little laser pointer. You can see how the magnetic field lines kind of ring around the bigger feature. You can see here they're around that direction. They kind of make a loop. Down this direction, they're primarily across. So there is structure to these. The star formation that's going on there is affecting things and giving a structure. And the dense clumps are very magnetic there. You can see down below, the purple area has strong magnetic fields. So the magnetic fields are doing something to the star formation. And it turns out they quench it. They actually are able to kind of hold the gas in place and prevent that shock that we thought should be making more stars from creating those stars. I should turn off the laser pointer. My mouse fell off my lap here, though. That's why we have a laser pointer floating around randomly. So anyway, these magnetic fields shut down the star formation, and it's interesting. So maybe that first simulation should have the magnetic fields hold the gas in place a little bit more, and maybe they'll get the right numbers. Who knows? Now, if this sort of stuff, if you like it, you should check out a book by NASA that came out. It's an ebook. It's a free ebook called The Lives of Stars, and you can download it straight from NASA. Our moderators in the chat hopefully have a link to put it in there. They'll put it in the chat down there and you can find it. But there's all sorts of interesting information, everything from gravitational wave sources and all the stars that we see within clusters and things. So free book from NASA if you like star formation. So Patrick, you have an interesting story here about some measurements that were made recently. What's going on with these?
Yeah, so this image here is actually an artist's conception of the solar orbiter. It's a European Space Agency mission with a lot of collaboration with NASA. And you may have heard, we've done stories on this, of the Parker Solar Probe that is sent very close to the sun to study the sun's corona. Well, this spacecraft is a complement to that because it will actually go as close as the, actually just kind of closer than the orbit of Mercury, about 26 million miles, and experience a temperature of 900 degrees Fahrenheit. But it's loaded with instruments, and we're going to go ahead and go to the next slide here and just show you its typical orbit. Here is just close to the planet Mercury. This spacecraft has a lot of instruments, and we're going to feature 3 of them because they were very instrumental to observing a coronal mass ejection, which is an enormous eruption from the sun. So one of the first instruments is this one, which is called the Extreme Ultraviolet Imager. And this basically captures layers of the atmosphere just above the visible surface of the sun, or what we call the photosphere. And you get an image kind of like that. It looks very pretty, but it's in ultraviolet light. Now, the next image, or rather the next instrument, captures the corona, the outer atmosphere of the sun, just above the coronosphere. And this is a little bit further out. This is roughly a view, that kind of reddish part there that you see in the image surrounding the ultraviolet image. It's a coronagraph, so the sun's visible portion is blocked out by a occulting disk, and we see the faint outer corona of the sun in visible light and also in ultraviolet light. And then the third instrument is this one, which actually observes visible light further away from the sun. And this one is observing the corona of the sun from 2 to about 18 million miles away from the surface of the sun. So putting all these 3 instruments together on February 12th of 2021 this year, all these instruments simultaneously observed a eruption from the sun. And we'll go ahead and look at this movie here, combining all 3 instruments. And within that red circle, you see a tiny puff of energy, actually material that's released from the sun. And the next instrument, which is the METRIS coronagraph, you can see the material moving further out, and finally, much further out, up to about 18 million miles in this 40-degree view of the sun. You can see the material ejected out from the coronal mass ejection, which are particles basically that make up the solar wind, but are traveling about 1 million miles per hour from the sun and out into space. This is a close-up image of it, so we can see how that material is moving from the sun. Now this diagram actually is a kind of like a simulation, so it looks kind of like a spirally thing on the left there. That shows the sun, which is that white dot in the middle. The red diamond shape is where the solar orbiter was. And then if you look at the 1 and 2 o'clock position, you see the material ejected away from the sun in that large coronal mass ejection. So this is a very interesting observation, and it's one of the early observations from the spacecraft, which was just launched last year. Some of the instruments are still being calibrated, and in the next few years, we'll get some really detailed images of the sun from these instruments and other instruments on board the solar orbiter. This will obviously provide us with more details on the activity of the sun, and also the coronal mass ejection, which is the mechanism which is kind of not well known at this time. So more images to come and more data and discoveries from this spacecraft.
Well, very neat stuff, Patrick. Thank you for sharing that. And, you know, coronal mass ejections, those are the sorts of things people kind of fear when they head towards planets. They can cause destruction, they can cause mayhem if they're really large. Satellites need to take cover. And it's these sorts of events that actually can affect planetary atmospheres or exoplanet atmospheres. Here's an artist's rendering, a pretty well done one actually, of sort of the core of a bigger planet that got stripped away. All the atmosphere got stripped, leaving behind probably a rocky metallic core. You could see it's hot probably, it's very close to its star. So, you know, a very, I don't know, a place you wouldn't want to hang out at. And maybe it's that sun, that star off in the distance that was sending those blasts off and clearing it. And in fact, we think that sort of action is indeed responsible for something that we call a gap in the distribution of exoplanets. When you look at exoplanets and you bin them, so you take the relative size, and down below is the size relative to Earth, so Earth would be here at a 1, and then the number of planets, the exoplanets really, per 100 stars that we think are out there, and this is based upon measurements. You get a diagram that looks like this. Now this first little gap here might be real, might not be, could be the way it's been, but it's this second gap that the laser pointer's in between here. That's real. That doesn't go away no matter what we do. In fact, the more data that are taken, the bigger and the more distinct that gap has become. And it's between something we call super Earths. Kepler, what is that, 452b, is 2.5, 3 times the size of Earth. It's bigger than Earth. It's larger, more massive. But then Kepler 22b is a little bit like a mini Neptune. So why is there a gap between? Why isn't that a smooth distribution between those? What in nature is making that happen? Well, what we think is happening is indeed the sunlight is making the planets change. So you have a gap, and as the planets, as the gas envelope gets eroded off that core, the planet actually moves from being a mini Neptune, will, what they say, jump the gap and become a super Earth. Now, what is the evidence for this? You might say there's no evidence. This is craziness. Well, people dug into the data. We now have enough exoplanets, we can start to group them together. The Kepler telescope, TESS is now giving us even more. We look at the data, we bin it. And it turns out the planet radius, again, is down below. Earth is a 1 size. Planet density, ignore that for right now. We don't need to worry about it too much. What you need to see is that pink region. And then how it moves, that green dash I'll put around it, with age. It's located in the pink spot when they're young. When they're older, it moves to the right and gets larger. All right, so what's going on there? What's going on there? What's happening is indeed the planets are shrinking with age. The star is blasting that planet's atmosphere, and the planet actually changes size. So the very young ones, you have more of these mini Neptunes and smaller super Earths. The older ones, the smallest of the Neptunes got transformed into a large super Earth. So the gap actually moves, and they're seeing that gap change position with time. So in a very, very young cluster, the gap is actually in a smaller position. In an older cluster, the gap has moved different. Well, I don't know if they're doing it in clusters, but they have to age date the stars. So really what's happening is the planets are being transformed with time. So this is kind of complicated. With exoplanets are changing what they look like over time. It's super interesting to study, but it becomes hard to understand. Also, the core of the exoplanet itself can affect the gas loss rate, the mass that's there, the gravity that's there, and of course, how bright the star is. The star might cause variability in the rate the gas is lost. So yeah, Neptune, in the right system, at least not in our solar system, could be transformed into, well, a super Earth, certainly not an Earth. So very, very interesting stuff.